To understand the specific shape of a cooling tower, you first need to understand why they are needed. A nuclear power plant does not generate electricity through anything exotic. At its core, it is a steam engine. Inside the reactor, uranium fuel rods undergo nuclear fission. Atoms split apart, releasing enormous amounts of heat. That heat is used to boil water into high-pressure steam. The steam is then directed at a turbine, a large set of spinning blades, and the force of the steam turns the turbine. The turbine is connected to a generator, and the spinning motion produces electricity. The nuclear reaction itself never touches the electricity. It simply provides the heat to make steam, and the steam does the rest. Once the steam has passed through the turbine and done its work, it has to be dealt with. And this is where cooling towers enter the picture. After passing through the turbine, the steam has given up most of its energy, but is still hot and cannot simply be released or reused immediately. It needs to be condensed back into liquid water, so the whole cycle can start again. To do that, the steam is passed through a condenser, essentially a large heat exchanger, where the steam meets cold water running through a network of pipes. The cold water absorbs the heat from the steam, turning it back into liquid water that can be pumped back to the reactor. The cold water in the pipes itself, now heated from this exchange, then has to go somewhere. Where a natural water source is available, a river, a lake, or the ocean, many power plants simply draw in cold water, run it through the condenser, and return the warmed water back to the source. It is simple and requires no additional infrastructure, but natural water sources are not always located where power plants need to be built, and environmental regulations increasingly restrict how much heat can be discharged into rivers and lakes. When neither option works, a cooling tower takes over, recooling and recycling the same water in a closed loop on site, independent of any natural body of water. A cooling tower works entirely through physics with no active cooling mechanism and very little energy. The warm water from the condenser is pumped to the top of the tower and sprayed downward over a structure of thin plastic sheets called fill, which breaks the water into a fine mist and maximizes its surface area. As the water falls, it transfers its heat to the surrounding air. This heats the air inside the tower, and hot air rises. As it does, it creates a natural upward draft that draws cooler, drier air in through openings at the base of the tower. That fresh air absorbs more heat and moisture from the falling water on its way up and exits through the open top as visible white vapor, which is simply water vapor, not harmful smoke. A single large cooling tower circulates millions of gallons of water per minute through this process, with a small percentage evaporating into the air on each pass. The shape of a cooling tower is called a hyperboloid, a surface that curves inward at the middle and flares outward toward both the top and the bottom, resembling an hourglass that has been stretched vertically. It is one of the most recognizable industrial silhouettes on Earth, and it exists for two specific engineering reasons. The first is aerodynamics. The wide base maximizes the intake of fresh, cool air. The larger the opening, the more air the natural draft can draw in per second. As that air moves upward toward the narrowing waist of the tower, the reduced cross-section accelerates it, increasing the speed of the upward draft and pulling air through faster. Then the tower widens again toward the top, slowing and spreading the warm, moist exhaust air as it exits, helping it disperse into the atmosphere rather than falling back down into the intake. Every curve in the hyperboloid shape is doing a specific aerodynamic job. The second reason is structural. Cooling towers are enormous, typically between 100 and 200 meters tall, and up to 150 meters wide at the base. A structure this large faces two constant forces trying to destroy it: wind pushing horizontally from the sides and the sheer vertical weight of the concrete pressing down. The hyperboloid shape resists both at once. A curved surface distributes stress across the entire structure rather than concentrating it at any single point. This structural efficiency means the walls of a cooling tower do not need to be thick. In most cases, they are between 15 and 25 centimeters of concrete, roughly the width of a standard brick, despite the tower standing as tall as a 60-story building. The shape is doing the work that material thickness would otherwise have to do. The hyperboloid design was invented in 1918 by two Dutch engineers, Frederik van Ittersen and Gerard Kuipers, who recognized that a curved geometry would simultaneously improve airflow, reduce material requirements, and produce a structure far more resistant to wind loading than any rectangular alternative. Their first hyperboloid cooling tower was built at the Emmer Colliery in the Netherlands that same year. The design was adopted almost universally within decades and has not been fundamentally changed since, because more than a century of engineering has not produced a better solution to the same problem. Click the video on your screen right now and I'll explain another everyday mystery you've wondered about your whole life but never thought to look up.